My name is Matteo Smerlak. I am a postdoc fellow at the Max Planck Institute for Gravitational Physics in Potsdam, Germany. The purpose of this paper is the study of stochastic processes in curved spacetimes. Understanding this general relativistic extension of stochastic mechanics is obviously relevant to gravitational physics, but also to graphene electronics, gradient index optics, and many other fields where the microscopic interactions can be subsumed under an effective curved spacetime metric. Generally speaking, a stochastic process can be represented by a so-called master equation, which describes the time evolution of the probability density function in terms of transition rates between different sites. Taking into account the fact that in a curved spacetime, time flows at different rates in different places, which is the phenomenon of gravitational redshift, I put forward a generalized master equation. For the case of diffusion processes, such as Brownian motion, this equation becomes the general relativistic version of the Fokker-Planck equation. One application of this result concerns dissipative hydrodynamics. Based on thermodynamical considerations, Eckert proposed in 1940 a generalization of the Fourier law for heat conduction that's valid in the presence of gravity, and he discussed the corresponding heat equation. Here I show that Eckert's heat equation coincides with the general relativistic Fokker-Planck equation. This result, if you wish, is analogous to Einstein's 1905 stochastic derivation of the Fick diffusion equation. In the case of thermal equilibrium, it gives back the Tolman-Ehrenfest relationship, stating that the product of temperature and lapse function is a constant in space. As another application of my results, I compute the curvature corrections to the mean square displacement of a Brownian particle in a spherically symmetric geometry. They are quite remarkable. Instead of growing linearly with time, I find that the mean square displacement can actually have an exponential growth rate in certain cases and to reach a finite limit in other cases, namely in the presence of an infinite redshift surface. I propose that these results may be used in effective spacetimes to tailor diffusive transport by a suitable design of the effective metric.